Welcome everybody to the 45th episode of Covalent Academy. I'm Valerie Brogdon and I'll be your host today for our webinar, which is entitled Unveiling the Nanoscale, PiFM for Chemical, Structural, and Surface Characterization. Our speaker today is Porg O'Reilly from Molecular Vista, and I'll be handing things off to Porg in just a couple of minutes. I just have a few housekeeping matters to share. So you can submit Q&A questions at any time through the Q&A tool, which can be opened from the bottom of your Zoom screen. And after this talk, I'll be sharing the recording and the slides on our website, and I'll give you more information about that later. So first of all, I just want to touch on a few things about Covalent Metrology. So at Covalent Metrology, we've built a modern, digitally empowered analytical services platform designed to help companies accelerate materials and device innovation. We offer a comprehensive solution stack with over 50 cutting-edge instruments and more than 150 techniques, supporting everything from analytical services and method development to advanced modeling and consulting. Our approach is high touch and high quality. We have programs like our Nexus membership that gives clients instant access to data reports and a growing suite of digital tools. And we're also flexible with how we work with our partners, whether that's through real-time collaboration with our Live View platform, co-op tool sharing, or customer training and certification programs. We've cultivated a rich network of partnerships with leading instrument manufacturers, including Molecular Vista and Thermo Fisher, Rigaku, Anton Par, Asylum Research, and many others. And this expands our clients' access to real-world technology and expertise. And finally, what makes Covalent special is our people. We're a team of more than 80 scientists and engineers, including 21 PhDs. We're headquartered in Sunnyvale, and we serve over 800 clients with 15 to 30 new ones joining every week. Together, we're setting a new standard for how metrology supports innovation. And this slide gives a sense of the breadth and depth of Covalent's analytical capabilities. We organize our work into several key technical groups, and each is led by experts who specialize in these techniques. So starting with electron microscopy, we cover everything from high-resolution SEM and FIB-SEM to advanced TEM methods with EDS, EELS, and diffraction. Our team also supports specialized lamella prep and 3D tomography for device cross-sections and nanoscale analysis. Our failure analysis team works closely with clients in electronics and semiconductors, performing everything from decap and cross-sectioning to emission microscopy, IR imaging, and root cause analysis. On the microscopy and profilometry side, we handle optical and laser-based imaging, including white light interferometry, confocal microscopy, and scanning acoustic microscopy for surface and subsurface inspection. Our analytical chemistry and X-ray characterization labs enable full compositional and structural insight using techniques like ICP-MS, GC-MS, Raman, XPS, and SEMS for chemical analysis, and XRD, XRR, micro-CT for crystallography and 3D X-ray imaging. We also provide a wide range of mechanical and materials property testing, from AFM to nanoindentation to rheometry, tensile testing, and thermal analysis, as well as surface and particle characterization like porometry, zeta potential, and DLS. And finally, our optical characterization group offers FTIR, UV-Vis NIR spectroscopy, and advanced ellipsometry for thin film analysis and optical modeling. Altogether, this suite of techniques allows us to tackle challenges that span everything from fundamental science to complex device engineering. So before we dive in, I'd like to introduce our speaker for today, Porg O'Reilly. He is an application scientist with Molecular Vista. So Porg joined Molecular Vista back in 2017 as an applications engineer and quickly advanced to his current role, where he collaborates closely with customers to design experiments using advanced AFM techniques. He has deep expertise in EFM, KPFM, and especially in Molecular Vista's proprietary Photo-Induced Force Microscopy, or PiFM, which we're going to hear about today. This is a powerful tool that combines the spatial resolution of AFM with the chemical sensitivity of IR spectroscopy. Porrick has logged thousands of hours of hands-on PiFM work across a wide range of specimens, from polymers and thin films to semiconductor devices, and his experience spans both visible and infrared PiFM, with particular strengths in semiconductor defect and contaminant analysis. So we're really excited to have him with us today to share his expertise and show how PiFM is transforming nanoscale characterization. So with that, I'm going to hand it off to Porrig. So I'm going to stop sharing my screen, and Porrig, you can go ahead and start sharing yours.
Sure. Thank you very much, Valerie. Okay, and thank you all for joining. So my name is Porrick O'Reilly. I'm an application scientist at Molecular Vista, and today I will go through a few things about us as a company and our technique, PiFM or PiFM. So this will include some general examples of PiFM results, comparisons with other techniques, and how PiFM can complement these other techniques and in some cases outperform them. I'll also show PiFM's performance on monolayers, which is essential for methods like anti-stiction and self-assembled monolayers. Okay, so we are an AFM IR company based in San Jose, California. Our patented technique is called Photo-Induced Force Microscopy, or PiFM or PiFM, which I will go through more in a moment. We design and build all our instruments at this site here in San Jose. So some of the history of the company, mostly in terms of the different tools that we have released. So founded in 2011 by Dr. Sung Park and Dr. Kumar Wickramasinghe, based on a technique invented by the latter. The first tool was released around 2013, which was then upgraded in 2016 to include its own IR laser for IR PiFM, which has been the main use of the tool since then. We then moved more towards wafer-compatible tools, starting with the 75, which has a 75 millimeter stage movement for 4-inch wafers, up to the Vista 300 for 12-inch wafers. Now, all of these latter tools here are CLARF compatible, so this is for navigation on blank silicon wafers. We have multiple laser options as well, including visible light sources, but mostly we use two IR lasers, one that covers the fingerprint region, and then another that includes the functional groups as well. So I'll go through what the tool consists of and how the technique works, but first we'll take a look at some other common analytical tools that are out there. So this table summarizes the current landscape of common analytical techniques. We have two general groups here that are separated by the species detected. So on the right side here, we have techniques that collect elemental information and these have high lateral resolution, but elemental information is limited, especially when looking at organic defects and sort of thin residues as well. Then on the left side, we have the molecular information techniques. Now these can identify those defects I just mentioned, but they don't have the resolution needed for the nanoscale. So the goal of PiFM is to take the molecular information benefits of something like FTIR into the realm of these resolutions comparable with these elemental techniques. So why IR? To gather molecular information, FTIR is typically used. It's really, what they say, the workhorse of the analytical chemistry lab. So all molecules will have a unique chemical fingerprint based on the vibrational modes of the atomic bonds present. So the advantage of IR is that you get detailed spectra for analysis and identification. And also with large databases for comparing spectra with. Now the disadvantage is that the resolution is diffraction limited. And this is where we turn to PiFM to determine molecular information beyond this diffraction limit. So to break this limit, we couple an IR laser with an AFM. So for those not familiar with AFM, fundamentally you have a cantilever, with a sharp tip, which is scanned across a surface and detects changes in the topography. Now, in this cartoon, you see that we also focus this, what we call the PIF excitation laser, at the tip sample interface via a parabolic mirror. And so in terms of this presentation, this laser will be an IR laser, and the power at the surface will be somewhere between 100 to 1000 microwatts, so, which will not damage your sample. It won't be strong enough to do that. And the upshot of this is that we take the spatial resolution of IR from 10 microns or so to less than 5 nanometers. So on a slightly deeper level, PiFM is a non-contact bimodal AFM technique. So being bimodal means that we can, so being non-contact means that we will not damage or contaminate the sample. And being bimodal means that we can simultaneously record the standard AFM information, such as topography and phase and whatnot, along with chemical maps. So bimodal uses the first and second mechanical resonance modes of the cantilever for these measurements. These are eigenmodes, meaning they're independent of each other. And the PiFM signal is generated using frequency mixing. So one of those frequency signals comes from the cantilever being oscillated at its second resonance mode of the cantilever. The other frequency is from the IR laser. And the frequency used for this is chosen so that a sideband is then produced that matches the first resonance mode of the cantilever. And therefore, any changes in the PiFM signal at this frequency is detected by the tip and then amplified by this first resonance mode. So again, we're using two eigenmodes of the cantilever, so we can simultaneously collect topography and chemical information. So in this example here, the IR laser is set to one wave number. The tip is scanned across the surface. Then any region that has an increase in absorption at that wave number will appear brighter in the map, meaning we can highlight the locations of specific chemical species. Then you can go ahead and change to another wave number and do the same, and to a third, and then you can sort of combine these images as well if you want to, and you'll see the locations of the different chemical species across the surface of your sample. Now, the other way of measuring the chemical information is via a spectrum. So in this case, the tip is moved to a specific location on the sample surface. The IR laser is swept through its range, and the response of the cantilever is recorded. So the stronger the response, at a specific wave number, the taller this peak in the spectrum will be. And this is directly related to the FTIR spectrum, which is what we see here. So there's excellent agreement between the PIF-IR spectra, which is the term we use for our spectra, and FTIR spectra. So this means, so you can see here the solid spectra are PIF-IR spectra and the dashed spectra are FTIR. And you can see all the peak positions and ratios match up. So this means that we can use the vast FTIR spectra databases that already exist and have existed for decades. We can use this to identify compounds using our PIF-IR spectra. Now, when we come back to this table, we see that this glaring gap that existed for high resolution molecular analysis is now filled by PiFM. Okay, so in this section, I'll go through some general PiFM results to give you an idea of its versatility, but also to give an idea of the experimental workflow. So again, this is an AFM-based technique, and here we have we start with a topography image. You can see a number of particles across the surface here with some variation in the size and the shape. So we have a number of options here. You can take spectra on all of them, or you could use chemical mapping or PiFM imaging, as is the term we use, to speed this up, especially if you have a large number of contaminants. You don't want to be taking spectra on every single one. So let's start with taking a spectrum on one defect. And here we see we have multiple peaks for this defect. We can select one of these wave numbers to take a PiFM image. In this case, we'll use the strongest peak, around about 1730 here. And we see that about 10 of these contaminants are highlighted at this wave number. So it's safe to assume that these are the same material, but of course you could take more spectra on them just to make sure. Now we also know the particles that are dark in this image do not have this wave number, so they're different material. Then we can go ahead and take a couple of spectra on some of these. And now we see that we have at least two additional components here. These are the red and green spectra. Then we can go ahead and choose wave numbers that are stronger for these materials and map those, which is what we see here with these two guys. And we can go ahead and then combine these images. And now we see that every particle that was in the topography image is highlighted in the combined image. So this means that we have very likely identified all of the components in this area. But of course, again, you can confirm by taking more spectra. And then finally, we can run these in IR databases, these spectra, and we can identify the contaminants as PMMA, PS, and PTFE. So this is just kind of showing the general workflow of a PiFM experiment, but it also shows one of the strongest uses of PiFM, which is to identify nanoscale organic contamination. So not only can PiFM ID organic contaminants, but also inorganics. In this example, we have a particle on a silicon wafer. The green spectrum is taken on the substrate, and the blue spectrum is taken on the contaminants. Interestingly, the wafer also has a very thin layer of contamination too. There are many more peaks here than one would expect for a clean silicon wafer substrate. Now we can run these spectra again in IR databases. And we found that the tin contaminant on the wafer is a silicone, so a siloxane-based compound, which is actually something we find quite often on wafers. And the particle is identified as silica. So this is most likely remaining from a wafer process like CMP, but I believe it's also possible for small silica particles to make it through ion exchange resins in ultra-purified water. So it could be remaining from some rinse as well, perhaps. So again, this is one of the most powerful uses of PiFM, looking at nanoscale defects, even inorganic ones. So analysis of polymers is something that PiFM has been used for since the beginning of the company, essentially. Here we're looking at a polymer blend solar cell in this paper released in 2018. And so from the FTIR, we know that the donor polymer has a stronger peak around 1453 and the acceptor around about 1706. So we can use these for PiFM imaging. The top row here shows your shows topography and phase images. Again, these are standard for AFM. And the PiFM images here show the separate donor and acceptor components in green and red, respectively, in this 1 micron region. We have them combined here. Now, the goal of this study was to see the impact on the donor domain sizes upon the addition of CN, so 1-chloro-naphthalene. Now, from these PiFM images that are taken at 1453, again, which highlight the donor component, we see that as you increase the concentration of CN, the domain sizes decrease. So, for example, the top left here is showing the lowest concentration. The bottom right is showing the highest. You can see a clear change in these domain sizes. So they also used resonant soft X-ray scattering to measure the average domain width and compared these results and those from PiFM with the cell performance. Now these are plots B and C showing these results. B shows the short circuit current and C is the photoactive volume. We can see from the measured width so this is the scale, the bar here on the left side, y-axis, that the domain size for PiFM tracks very well with the cell performance for both of these measurements. You can see the bottom black line here is PiFM. It tracks the red line here and the blue line here. Whereas for ORSOX, it diverges for the larger domains. So this is an example of PiFM being compared with results from another separate measurement technique and where it seems to perform better. So in this section, I'll go through a few more of these techniques where PiFM is used to complement and in some cases outperform standard analytical techniques. So first, we're going to look at copper oxide and XPS. So this is essential for hybrid bonding, where the nature of the oxide impacts the efficiency of the bonding of copper pads. The top two plots here are reference XPS plots for copper 1 and copper 2 oxides. Now, from looking at those taken on the spectrum, which is this bottom row, these taken on the sample, which is this bottom row, we see that sample A consists of copper-1 oxide and sample B of copper-2 oxide. So one of the limiting factors with XPS is its relatively poor lateral resolution, which is in the realm of microns. So therefore, XPS will not be able to investigate individual small pads, especially if they have small pitch sizes as well. So again, this is where PiFM can come in. So for PiFM, we can use the FTIR of these oxides as references. Copper-1 oxide shows a strong peak around 620 or 619, as it's highlighted here. So we can use this wave number for imaging the sample. Here on the right side, we have the PiFM images. So these are the chemical images, which are at 619 and therefore highlighting copper-1 oxide. And it's clear from these that sample A is showing a much stronger signal than sample B is. And this matches what the XPS showed. However, as I mentioned earlier, due to the sub 5 nanometer resolution of PiFM, it can be used to measure individual pads, but all on a wafer, but also any variation within those pads themselves. Now, for this study, PiFM was used in conjunction with TEM tomography. This sample is a cross section of a wood cell. From the FTIR, we see that cellulose, which is this green spectrum, has a strong broad peak around 1100, while the blue spectrum is lignin, which increases below 1300, probably most notably around 1500. So these bands then can be used for mapping these components using PiFM imaging. Now you can see from these images that the overall composition of this area of the cell wall is these two components. So it's cellulose in green being these sort of outer regions, and the lignin in blue, dominating the inside regions. Now we're interested, they were interested in seeing how this looks more zoomed in, so around where this gold arrow is, because you can see sort of green sprinkled within the blue here. Now, when we zoom in and take a topography image, there is some evidence of these sort of bumps on the surface. So these are going to be lighter in color, which represent taller in topography. Now, our chemical maps on this show that these bumps that are in the topography are cellulose, while the surrounding area in blue here is lignin. Now, there's actually also very small cellulose areas in the chemical map, so these green guys here, that cannot be discerned from the topography alone. And the spectra also confirmed this. So with the green area showing this strong broad peak centered around 1100, and the blue increasing below 1300, which is what we saw in the FTIR reference spectra. Now, the TEM tomography that they did indicates that there are these elementary fibrils running through this part of the cell. And the composition of these fibrils, as we just showed, are cellulose. So PiFM not only detects the fibril bundles, so these larger bright areas, but also elementary fibrils, so these smaller bright areas, and these are less than 5 nanometers in diameter. So the TEM tomography was actually carried out on a different sample than the PiFM measurements were in this case, but it still shows how it can be used to complement data from another technique and to sort of build upon these models. So in this example, we show how PiFM can be carried out on the same samples used for TEM. Ascorbic acid is dropped on a TEM grid and recrystallizes. 4D STEM shows that the recrystallization results mostly in two prominent orientations. So the results shown on this slide are a general example. The crystals shown in the following slides are part of an ongoing study. So we can mount these TEM grids on AFM disks and use the grid structure then to navigate to specific crystals to measure known locations. So you can see from this TEM image that the same region of interest has been located in our microscope. I'd like to mention here actually that we recommend PiFM being carried out first because electron beams can contaminate some samples and even ablate them. Now we see this more with SEM and EDS, but it is worth noting here too. So as we zoom in on this crystallized region to a 10 by 5 micron section, then we took spectra in sort of a line across it. Now, there are a lot of spectra here, so the variations might not be immediately obvious, but they were primarily around 1730, 1670, and 1140. Now, if we just look at a few of these spectra, you can see this more clearly. So around 1730, the change here is very subtle. So the blue spectrum here is slightly taller. But we can clearly see the peaks around 1670 and 1140 increase for the green and red spectra, respectively. Now, we've also taken PiFM images at these wave numbers. And then when we combine these, we see that they mostly highlight different regions, different locations. So this seems to be indicative of different crystal orientations. Now, the reason that PiFM can see this is the laser light that's used for PiFM is p-polarized with respect to the surface, and therefore it's along the tip, like with these arrows are showing. So PiFM is most sensitive to modes that are normal to the sample plane. So that is why PiFM can show variations in molecular orientations, especially in the rigid orientations of crystals. So as mentioned before, this is an ongoing study. So they are still modeling this to see which modes might be represented by each absorption band. But hopefully it gives you an idea of how PiFM can be used in this way when it comes to molecular orientations. So for SEM and EDS, most of our examples are from defect review wafers, so I can't show that data, but I want to make some sort of general comments on this. SEM EDS is used as the primary tool for wafer defect analysis. And while it's very powerful, on the chemical side, it will only give elemental information, which is not ideal for ultra-thin residues or organic contaminants. But also SEM and EDS can contaminate the sample, so which can be seen here in my relatively crudely drawn image. But we usually see these sort of square burn marks around the SEM scan area, but we also see circular EDS marks around the defect. Then due to the higher electron beam power used for EDS, we commonly find the defects ablated into smaller particles, and in some cases, the defects are completely gone. So as you move towards smaller defects, it's more likely that the EDX is going to remove them completely. So while SEM can be useful, we strongly recommend that you use PiFM first, since it's non-destructive and also CLARF compatible. So a brief note on what I mean by CLARF compatible. So a wafer inspection tool such as SurfScan from KLA uses lasers to quickly scan a wafer and create a file with the coordinates of defects of the defects that it detects. So we can take these files and load them into our software and navigate to these coordinates with sub-micron stage accuracy. We've also developed an automated mode that will navigate to user-selected defects for you. It will take an image, and then it will move to the defect and take a spectrum. It can take a spectrum off the defect if you want. And then it will move on to the next defect and repeat. Now, our current capability is 1 to 2 minutes per defect. We're hoping to bring that down, obviously. So as the critical dimensions continually decrease in the semiconductor industry, the effectiveness of EDS for identification will be more limited as we become more interested in these smaller and smaller contaminants. So this is where PiFM can fill that gap. So another application that PiFM is extensively has been used for is investigating resists, with EUV latent imaging being the most prominent recently. So this specific resist is under IP, so we will not show any spectra of which wave numbers were used. But we can go through the experiment and how it compared with other analytical measurements. With these more sort of zoomed out images, it's easy to see the unexposed regions since they are taller, so these lighter colored lines and this number here. So we simply move the tip to one of these raised regions and take a spectrum that will show us the unexposed area or the unexposed spectrum. And then similarly, we move to a lower region and take a spectrum on the exposed regions. And we're going to refer to the wave numbers used for imaging as wave numbers A and B. So wave number B, we see highlighted the regions that are taller in topography. So again, this is the unexposed regions. And wave number A highlights the exposed region. So in this zoomed out image, it's kind of easier to see what it does not highlight. So this is the unexposed 12 and these larger lines. But when we zoom in a moment, it'll be more clear what the exposed regions look like. And finally, we can overlay these two wave numbers and show that wave number A is brighter where B is darker and vice versa. Okay, so now that we have these sort of good wave numbers for the exposed and unexposed regions, we can zoom into the much smaller lines in between these two larger lines here. So here we have the topography images for the exposure and post-exposure bake samples. So the first thing you might notice here is that these features, these lines, essentially disappear after the bake. So AFM alone will not tell you much about the post-exposure bake sample. However, we can still see the chemical contrast in PiFM, even for these 12 nanometer half pitch lines. Now, when we look at the line profiles across these, we can see some interesting things that might not have been immediately obvious. So these line profiles were averaged down the entire length of the images, and there's two things that I kind of want you to focus on. So as I briefly mentioned in the previously, the green line here shows the post-exposure baked topography. So again, it doesn't show obvious topographical patterns, but the chemical maps do. So this is for the red and blue lines. And so PiFM can detect something that standard AFM cannot. And secondly, the purple line here, which is highlighting the exposed parts of the exposure only sample, shows this sort of double line artifact. So you can see that every second dip is shallower than the previous. You can also see this to an extent in the post-exposure bake sample, so this blue line, but it's less pronounced. And in fact, this artifact is carried all the way through to the developed sample. So here we have some SEM images that they took on the developed sample, gradually zooming into this 12 nanometer half pitch lines. You can see from this zoomed in image, and especially from this line profile here, again, that every second dip is shallower than the previous. So this artifact was actually just a small misalignment of the illumination beam into the imaging optics, which led to every other line receiving slightly more dose than its neighbor. So the upshot of this is that it unintentionally highlighted PiFM's capability to predict the final pattern, including these unwanted artifacts. And you can see this as we overlay the wave number A profile from the exposed sample, so this purple line, on top of the developed SEM profile. So every second dip is shallower. So the other tool that was used for this study was CD ORSOX. So CD ORSOX offers statistical measurements over a larger sample area, and it captures the ensemble averaged periodic structural details, so topographical structure, but it also has sensitivity to specific chemical environments as well. So here we have the non-resonant energy plots for all three samples. Now these plots this energy is mostly sensitive to the topographical structure. So I want you to focus on the insets here, so where this gold arrow is pointing. And these display the 1D plots of the scattering intensity along the long edge, so where this gold dashed box is. And essentially, if you see these sort of scattering lines here, there are periodic topographical structures. So we see that the after exposure sample and the developed samples both show a strong scattering pattern, while the post-exposure bake does not. Now this matches what we've seen with the topography images during PiFM for the post-exposure bake and the SEM images on the developed sample, that after exposure and developed samples showed a clear topography pattern, but the post-exposure bake did not. Now, when we look at the resonant energy plots, now these are more sensitive to the chemical contrast, we see that the post-exposure bake sample now has a strong scattering pattern, similar to the other two samples. So again, this agrees with the PiFM measurement, where there was a clear chemistry contrast for both the post-exposure bake sample and the after-exposure sample, but only the after-exposure had a clear topography pattern. So this shows that PiFM results are confirmed by CD ORSOX, but also the PiFM can predict artifacts that will be in the developed sample just from imaging the exposed sample. So finally, I'll go through a few measurements on monolayers. So in this case, we are looking at a lube on a disc. So the lube is around 1 nanometer thick. The images on the left are taken on the lube sample, and these 6 spectra taken on the surface are shown in the top plot. The bottom spectra are on a bare disk, and you can see that even with this very thin layer, the lube spectra are reproducible and are dominated by peaks between 1100 and 1300 or so. And the PiFM image taken here in the bottom left corner is at a lubed wave number. And it looks like there are nanoscale variations. It almost looks like noise, but when we zoom in, we see that they are real. So these are 500 nanometer wide images. And you can see the brighter and darker regions in this PiFM image. And so the average spectrum for the substrate was actually sorry, so the average substrate spectrum is subtracted from these lube on a disc spectra, and you can see excellent correlation with the black neat lube FTIR spectrum. So even with this very thin layer of lube, we are getting FTIR-like results. Now the spectra taken on and off the bright regions on the PiFM lube sample, so these are the red and blue spectra respectively, they show a change in the lube peak intensities, and this is actually related to the thickness variation of the lube across the surface. Now when we overlay the topography here in green with the lube map in red, we see that the regions that are brighter for the lube map, so again these red, match regions that are darker in the topography image, which is green. So this tells us that the lube layer is thicker in the dips in the topography. And so again, even with this very thin layer of lube, we're actually still able to see the variations in its thickness. So this shows the benefit of PiFM for anti-stiction analysis, for example. Now finally, we looked at some more monolayers and some potential shortcomings of water contact angle measurements and ellipsometry when you rely on these alone. So polypeptoids, which are polypeptide-like molecules designed for binding to silicon, were used for this study. So initially starting off with the carboxylic acid binding group. So the monolayer is formed by spin coating a thin film, annealing it to produce the grafting reaction. So this is where the molecule will covalently bind to the silicon. Rinse the excess film away with solvent and then anneal again to remove this solvent. So as an initial test, water contact angle measurements were taken. On the left side here, this included the grafting steps, so they should have a monolayer on the surface here, and the right side did not include this grafting step, so there should be nothing on the surface. And the water contact angle measurements show a clear difference between these two. Therefore, it indicated that there should be a monolayer on the surface. So with that in mind, PiFM measurements were taken. So these images and spectra are on a thin film. It's kind of as a reference. So as expected, there is clear evidence of the polypeptoid, most notably with this carbonyl peak around about 1670. There are additional peaks around about 1260, 1100, 1020, and 800, and which suggests some siloxane contamination. Now, when we look at the monolayer samples, we see there's no evidence of this carbonyl peak. There are some siloxane peaks again and some CH peaks around 1460 and 1380, but definitely not a homogeneous peptoid monolayer. Now, but when we zoomed in a bit more, we see that there actually are some peptoid molecules on the surface. So while some of them are difficult to see in the topography, they can be seen in the PiFM image here at 1633. So these sort of slightly brighter regions that are in this chemical map. Now the green and blue spectra are taken on some of these brighter regions, and we see that there is this carbonyl peak. So this shows that while water contact angle measurements suggest that there was a peptoid monolayer, PiFM shows that there are only small submonolayer fragments. So then they revisited the composition of the molecules and they changed this binding group from a carboxylic to an OH group. Now, the interesting thing is here, they actually redid the water contact angle and ellipsometry measurements for this new OH monolayer sample, and it showed very similar results to those found on the carboxylic acid sample. So this, and that sample obviously did not have a monolayer. So it's not possible to discern from these results if there actually is a monolayer or not. It would actually suggest that there's not. So this is where we then return to PiFM. So we remeasured one of the carboxylic acid samples, this time using a laser with an extended range. But we see that there are still these sub-monolayer fragments, as we would kind of expect. So in this case, and you can see with the red spectrum is taken on one of these bright regions. Again, it has this carboxylic acid group, but the orange spectrum taken off it shows nothing. And from the map, we see the majority of the area does not have any of these peptoid molecules. But for the new OH formula, we see a monolayer. So the PiFM image map at 1648 shows there's some variation of the spectra. So the map does show some variation. So there's some brighter spots, some darker spots, but the spectra on the darker regions, which is the green spectrum in this case, still shows the carbonyl peak, but it's just weaker. So the change in this intensity is most likely due to changes in the packing density of the molecules in the monolayer, but we are seeing pretty uniform coverage across the surface. So finally, these monolayers were patterned using E-beam lithography. PiFM is used to highlight the peptoid lines, in this case at 1658. And the substrate is then highlighted at 1113. So this is the silicon substrate here. Now the spectra taken across these also show this with the peptoid peaks around about 1660 and 1450. And then every spectrum is showing the silicon oxide, a native oxide peak around about 1110. You can see from the topography here then that these peptoid lines are only about 1.5 nanometers tall, but they're easily identified with PiFM. So this shows the benefit of PiFM over relying solely on water contact angle and ellipsometry measurements. All right, so as a bit of a summary, we went through the basic setup of IR PiFM and what it can do. Again, this is an AFM-based technique, so if you can do AFM on your sample, you can do PiFM. It has excellent spatial resolution and monolayer sensitivity, which can be used to chemically map and identify organic and inorganic compounds. It is CLARF compatible for defect review and non-destructive, so it can complement other metrology techniques. So I'd like to thank these folks here for their sample preparation and all the other measurements done on their samples. So without them, we wouldn't be able to do this today. And thank you for your time. Feel free to contact us for any additional information via the email address here or check out our website. Thank you.
Thank you so much, Porig. That was really great. I definitely learned a lot. And thank all of you who attended this webinar for your time. And you can feel free to contact us for any additional information. So I hope this presentation gave you a sense of just how much you can really do with PiFM. If you need help with advanced nanoscale characterization capabilities, or if you want to discuss a potential future project, we're offering free discovery consultations with Covalent experts. So you can schedule the appointment through the link in the chat. And if you want to reference or review these slides or this presentation later, you'll be able to access all of the materials for this episode and all of our other episodes at academy.covalentmetrology.com. And with that, I'd like to introduce Austin Barnes, who is Covalent's Director of Materials Chemistry and Surfaces. He will be helping us with the Q&A session. So now we can get started on the Q&A. And I noticed there were a lot of great questions already in the chat that Austin's been helping to answer. But
Yeah, thank you. I tried to do my best during your talk. So thank you everyone for all of the really thoughtful questions. I got one question that I had a little bit of difficulty answering. And Porrick, I was wondering if you could if you could have some help to answer this. So I got a question that's, what's the typical free amplitude of the cantilever used for PiFM measurements? And how does that affect resolution?
That's a good question. So we set the free amplitude to about one nanometer. Our height above the surface is a few nanometers, and whenever we basically snap into that sort of attractive regime. And now with changing that free amplitude, we haven't really done extensive studies on this, but we do believe that the probing depth would possibly increase with that sort of higher free amplitude. Um, because you're tapping harder, so it might sort of increase the depth of that. With the lateral resolution, I don't think we've seen any big changes in that. Yeah, now we do also have, when I do mention the sort of probing depth. So in everything I went through here in the slides is in what we call our sort of surface sensitive mode. So that's going to be with the 20 nanometer sort of maximum probing depth, but mostly sensitive to the first few nanometers. We also have another mode that we call the bulk mode, and that's more of a sort of hundreds of nanometers deep into the sample. So if you're thinking of probing deeper into the surface, you can use that mode instead of, let's say, tapping harder. But I think if the tapping harder does increase your probing depth, it's not at that scale. It wouldn't be hundreds of nanometers more.
I had a question kind of as a follow-up to that. If you had say like a conductive sample, um, say like a uniform metal film versus like if it's a dielectric, like a polymer film, how does the photo-induced force change between these two different cases?
Sure. No, another good question. So so we use a metal coated tip. I don't think I mentioned that in the presentation. And the reason we do that is because it gives you field enhancement with the laser and the metal coated tip. Similarly, if you have a metal coated surface, you're going to increase that enhancement even more. So from an experimental point of view, you need to use lower laser power in order to get a decent PiFM signal. And now, obviously, if you're just looking at pure metal coated surfaces, there won't be an IR response. There will be for metal oxides. But if you're looking at let's say a pure metal coated surface with a thin polymer film, like with some monolayers on it, you will get enhanced PiFM signal. So it will increase, again, it will increase the PiFM signal, but it also might increase that probing depth, even in sideband mode, because you're going to have the enhancement of the tip and the metal underneath to sort of increase that.
So let's say like maybe if we had a mixture of like a polymer material on top of a conductive type of material, you'd probably recommend trying to land the probe on the polymer, try to play with the laser power settings a little bit so we're not getting too much contribution from the conductive regions as well in the scan.
Sure. What I would probably recommend is you'd actually optimize your laser power on the metal. Well, here's the thing. If in your example, are you talking about a polymer on the surface and underneath you have, like, let's say metal lines, but the polymer is over everywhere?
It could be like a battery material, like an anode.
Right. Well, what you can do in that case is if you do have, let's say, a mixture of metals and other materials, we do have something that's called notching. So the thing is, as I mentioned, you will have that enhancement of the PiFM signal on metal areas, but it might just be a specific wave number, which could be the silicon oxide peak of the tip itself. So underneath the metal coating, the tip will have its own native oxide. So what can happen is when you're on a metal, you have that enhancement, so you actually can see some of the native oxide itself. But using notching, you can basically cut the power down for any band that you want in the sample surface. So for the laser power used for PiFM, we can control the percentage of power that we use across the range. So you can notch out these stronger peaks on the metal in order to kind of have a safe scanning across all of those different materials.
Mm-hmm. And so like, I don't know, how does surface roughness play a role in how does it influence the PiFM signal?
So there's no impact between the topography and the PiFM when you're looking at sort of normal samples. Because we use, again, it's a bimodal technique, so we're using the second mode to track the topography, so that keeps the tip sample distance very well. We also use a dual scanner mode, so we have for the scanner in the stage for the topography, we also have one in the head, so that means that we maintain the tip sample gap quite well. However, if you're looking at very tall features, then if with a high aspect ratio, as the tip is going up the edge of these tall features, obviously the tip will not be quote unquote engaged with the sample at these, so you will get a drop in the PiFM signal along these sort of sharp edges. But then across the surface, there will be no issues.
Mm-hmm. One question I am fascinated. It's crazy how you can get lateral resolution that's less than 5 nanometers, especially like some of these tips, right? Like these are platinum coated tips usually.
Sure.
So there's the radius of curvature is around 20 nanometers. So how can that be where the lateral resolution is actually better than the topography itself?
Yeah, no, exactly. So basically with the, can I briefly show my screen if that's okay?
Yes.
Let me pull up one of the slides that was in the, okay, one of the slides that was in my presentation that might show this a bit more clearly. Okay, so this kind of shows it a little bit here. I didn't really go into it that much, but we have so basically at the tip apex, what we were seeing is we kind of formed this, what we say, hotspot right at the tip apex. So where you have the laser focused at the tip sample junction, the tip sample interface, we effectively have a hotspot right at the tip apex. So that's actually what's measuring the PiFM. So when you have that frequency mixing between the tapping of the cantilever and the IR laser coming in, basically the PiFM signal will only occur when they're kind of right beside each other. So essentially that's exactly where we're measuring the PiFM response, whereas the topography we're doing sort of the larger area of the tip itself. So we have effectively a smaller tip size for PiFM.
Got a couple other questions here if there's still time. I got one about speed. So
Yes.
AFM is traditionally a bit of a slow scan. So if I've got a defect on a wafer and you're reading a CLAR file, like what's the typical like time span in order to read out exactly what the composition is of that defect on a wafer?
Sure, no. That's the always asked AFM question. I completely understand it. So what we've found is, so it's going to depend on your scan size, and it will depend on your pixel density, so the resolution that you use for it. So if you're not super interested in the fine details of the structure of the particle, you can use a lower resolution pixel density, so you can scan faster. So in the examples I show, I say 1 to 2 minutes per defect is what we found using our automated defect review. And that mostly comes down to whether we use, let's say, a 64 by 64 pixel density or a 256 by 256. So it will come down a bit to, and I don't want to get into this too much because I'm not super familiar with instruments like Surfscan, but I believe that some of the older generations might have a bit more variation in the accuracy of the positions of the defects compared to the newer generation of things. So if it's, if there's a variation of just 1 or 2 micron, then you can do a smaller AFM scan. But if that variation is a bit higher, then you might need to do a larger AFM scan to make sure that you find the defect. So our stage accuracy is really good. It's sub-micron, and we're trying to improve that as well. But with the coordinates themselves, we don't know if there's a subtle variation in those. So I would say we can do the scans probably at the moment about 30, 40 seconds for topography, and then we do the PiFM spectra as well. We can do them to 5 to 10 seconds. Yeah, so there is, obviously it's not super quick compared to some other techniques, but I would say it's not bad as AFM goes.
Okay. I'm still getting quite a few questions that are coming in. I don't know how much time we have, Valerie.
We've got about 4 more minutes, so we can answer maybe 1 or 2 more questions.
Okay, so one question is about amplitude of the photo-induced, like the PiFM channel itself, not the topography. So, typically you said the amplitude of the second eigenmode is about 1 to 2 nanometers. That's what we use for topography tracking. Then what we're actually recording is the photo-induced force response, which is based off of the amplitude at its fundamental frequency.
Yeah.
And that is, typically due to the dipole moment that is induced into the material. There could be other forces at play that are going on, but what are the typical amplitudes in that PiFM channel that the cantilever is like typically seeing?
That's a great question. I'm not sure. I don't know it in nanometers. Now I know in millivolts that it's around about 1 millivolt. It's going to depend obviously on what your laser power is. We try to target it at 1 millivolt, but I'm not sure what that correlates to in nanometers. It's an excellent question.
Okay. So yeah, that might depend on the stiffness of the cantilever and how, like, what the optical lever sensitivity
No,
value
exactly.
is.
We could calculate it, but I don't have the numbers here on me.
Okay.
You can take
all right, that's all.
Question.
Okay, one more question. Okay, let's see.
Make it an easy one.
Yeah, I don't know if you can gauge whether or not it's an easy one because we only have about 1 more minute.
Okay, I've got a question about recording the spectrum of the sample at different wave numbers if the modulation frequency is fixed. I think this maybe is just a question about the tuning and sweeping of a frequency when you take point spectra versus the PiFM mapping mode. But could you elaborate on just those two differences one more time?
Yeah, so with the PiFM imaging, you're just choosing one wave number and you're scanning the entire range, and then the areas that contain that wave number will be bright and brighter depending on how strong that absorption is. And then with the spectra, we go to one spot and then we sweep through the range of the laser and record how the cantilever responds at those different wave numbers, but on one location. So that's what gives us that spectrum, is how it changes at specific wave numbers as we sweep through the range.
Okay.
Great, thank you.
Yeah, thank you so much. It is time to wrap up. Thank you all for joining us today. If you have any extra questions, you can reach out to us at Covalent. You can reach out to Poreg. And yeah, thanks again, Poreg, for talking to us.
Thank you.
All right, everybody, have a great day.
Bye-bye.